All right, so let's just recap for a minute. Probably most important virulence factors, we talked about pili. Those are going to be really important. We talked about capsules, and now we're going to talk about toxins. Toxins are extremely important. They're very tested on the USMLE Step 1 for microbiology. So we're going to spend a good bit of time making sure that you understand the different types of toxins we have, and then what's really essential for the exotoxins is that you know how they work. So what is the mechanism of action of those toxins? So what you see on the slide is that we have endotoxins and exotoxins, okay? Now, almost always students will get confused on the toxins. You don't want to do that. They know you're going to get confused. So almost always, if they're asking you a question about toxins, in the distractor list, you'll have endotoxins and exotoxins. They're going to bank on the fact that you're going to get confused. So don't do that. Don't give them that satisfaction, okay? Endotoxin, you want to write, is equivalent to LPS, which is lipopolysaccharide, okay? They're all the same things. They'll use them interchangeably. The key thing that you remember about LPS is that it's only on gram-negative organisms, all right? And I'll go through a vignette with you and show you how they're going to ask you a question about endotoxin and LPS, all right? Now, there's two different things that they'll typically like to ask. Number one, they'll give you a scenario where LPS was clearly involved, and they'll want to know what actually was the specific toxic portion of LPS, okay? And that's the lipid A portion. The rest of it is polysaccharide, it's just sugar, and while it's immunogenic, it's not really toxic. It's the lipid A portion that's extremely toxic, okay? Now, what LPS does is really overactivates the immune system. Think about the immune system. It is a system in your body designed to kill things that aren't supposed to be there, okay? So anytime you get this system really overworked and overactivated, there's always a chance that it's going to do nonspecific damage, and that's what we see a lot of the times with LPS. The key example I can give you about LPS is they'll tell you that you have a patient, they'll tell you signs and symptoms of septic shock, all right? And they'll tell you that they did blood cultures and they found a gram-negative organism. And they're going to want to know specifically what is responsible for the symptoms of shock, the fever, the hypotension, what specifically has done that. And if they told you that the person had gram-negative sepsis, they're asking you to tell them it was the LPS, okay? So in a case of gram-negative sepsis where the patient's going into shock, they ask you what the mechanism of that shock is. It goes back to the LPS or the endotoxin, okay? It's called endotoxin because it's within the outer membrane of the gram-negative organism, all right? So don't ever get confused between endotoxin and what we're getting ready to talk about, which are the exotoxins, all right? So now you know you will never get confused because you know I'll hunt you down and I'll find you if you get confused on these. Endotoxin on gram-negative. Exotoxins, which are secreted toxins, can be secreted from gram-positives and gram-negatives, all right? So good example, Staph aureus, toxic shock syndrome toxin, E. coli, the cyclic AMP-inducing toxin for gastroenteritis. So two examples where you have a gram-positive and a gram-negative, all right? So gram-positives and gram-negatives can secrete the exotoxins. Now, what is interesting about the exotoxins is that they are what we call AB toxins. So what you want to remember here, we've got alphabet soup here. So B binds. So remember BB, B binds. B is the part of that toxin that binds to the receptor, okay? And remember A, active, A active. So the B portion binds that toxin to the receptor, allows it to get taken up by the cell, and the A portion blasts the cell, all right? whether it's going to modify it, whether it's going to kill it. Lots of different choices of things it can do, but the A is what's going to accomplish that goal, all right? Now, there's all different types of toxins, and we're going to talk about those. What you see at the bottom are the cytolysins. All in all, relatively less important than some of the AB toxins we're going to talk about, except for when we talk about Clostridium perfringens, which causes gangrene. In that case, a cytolysin is directly why you get myonecrosis from Clostridium perfringens. Okay, so what we're going to do now is just look at some of the different toxins and their mechanism of action. Clearly, they're going to test this by giving you a vignette for each one of the organisms that you see listed here. They're not going to tell you the diagnosis, so they're going to make it a second-order question or maybe a third-order question. So they'll give you a case, and they'll want to know what the mechanism of action of the toxin is in the above scenario. All right, so it's really important that you understand how the toxins work. All right, now, as far as the different types of toxins, we've got protein synthesis inhibitors that we're going to talk about now. We have cyclic AMP inducers, and then we have the neurotoxins. Those are your basic categories. Superantigens are a little bit different, so we'll talk about those separately, and then the cytolysins, again, we'll kind of separate those out a little bit. The protein synthesis inhibitors function by one of two different ways. They're either going to interfere, as you see with diphtheria and Pseudomonas, with elongation, all right? So if you're interfering with elongation, you're not going to get a functional protein made. Or, as you see with Shigella dysenteriae, and what you'll see on the next slide, enterohemorrhagic E. coli, is that they interfere with the ribosome, all right? And you got to know specifics here, okay, for step one. So you need to know its elongation factor, and you need to know it's the ribosomal subunit. Now, who likes to tag on to this are the biochemists, because clearly micro is so much more exciting than biochem. They're going to tag on. They're going to pretend like this is a micro question, so you get sucked in, and it'll be biochem, and they'll want to know something about the ribosome or elongation. But anyways, you definitely have to know the mechanism. Now, what happens in a cell if you can't make protein? Okay? The cell's going to die. All right? So you're going to get cell death. You're going to get necrosis. If you look at each and every one of the organisms that are making these toxins, you can clearly see that that's happening. Let's go, for example, to Shigella dysenteriae, making the Shiga toxin. Shigella is like a double whammy for gastroenteritis. Like if you had to get gastroenteritis, clearly you do not want Shigella because it does the two things you most don't want. Number one, it invades. And number two, it makes a toxin that kills your cells. It inhibits protein synthesis. How does that translate? Bloody diarrhea, which nobody wants, okay? So that just kind of translates and shows you how those different toxins are going to come into play. You're definitely going to see these, all right? Now, the neurotoxins are also listed here. What's nice about the neurotoxins is they're both in the same genus. So we have Clostridium tetani and Clostridium botulinum. So both in the same genus, and they're the only neurotoxins. They're extremely potent, all right? So as far as injecting them into your face to smooth out wrinkles, personally, I don't recommend it. You're taking the most potent toxin known to man. It's like on the list of biological warfare agents. But go ahead, inject it into your face. I'm just going to age gracefully. All right, so for the neurotoxins, what you want to know is that they're almost opposites of each other, okay? You have tetanus toxin, which is a spastic type of paralysis, and then you have botulism toxin, which is a flaccid paralysis, all right? So if you can remember that, if you can remember botulism goes with floppy baby, which is clearly flaccid, then you can then remember how it works. So how is it going to be flaccid? It's going to block the release of acetylcholine, all right? And if you remember tetanus and the classic signs that you see with tetanus, with the arched back and they're very rigid, and there's any very painful spasms, you'll know that that's a spastic paralysis. And what do you need for a spastic paralysis? Then you can kind of work backwards so you don't have to necessarily memorize all of these things, but that you know how they work. So for tetanus toxin, they're blocking the release of your inhibitory transmitters. Therefore, you get these very painful muscle spasms at the very slightest stimulus. So even a whisper or someone turning on a light can send someone with tetanus into these very painful muscle spasms. Those are very important, and I guarantee you're going to see at least one of them on step 1 under the microbiology section. All right, superantigens. Okay, superantigens are really important. We will talk more about the mechanism of superantigens when we highlight the immunology, but superantigens function by basically overstimulating the immune system. So what do you see with LPS? We talked about LPS and endotoxin. Overactivates the immune system, okay? And what happens? The patient goes into shock, all right? With a superantigen, we're basically doing the same thing, all right? So with superantigens, by way of overacting this time T cells, which are going to activate macrophages, and we're going to get this cytokine storm that basically overactivates the immune system. And if you look at the role in disease, very similar: fever, shock, capillary leakage. So again, I can't stress enough, when you overstimulate the immune system, it's never really a good thing, all right? Probably the most tested is going to be staph as far as the superantigens. And I haven't heard anybody talking about the strep pyogenes superantigen because they still always usually go back to staph. So you definitely want to remember staph. Now, last of the specific toxins are the cyclic AMP-inducing toxins. So before we get into specifically the different organisms, just stick with me on how the cyclic AMP works. Normally, in a cell, you'll get a transient increase of cyclic AMP. What these toxins do is it chronically and consistently elevates the levels of cyclic AMP inside of a cell. When that happens, ions are going to go running out of the cell, and water is going to follow. All right? So look at the very first example, enterotoxigenic E. coli. Enterotoxigenic E. coli, what do you get? Massive, watery diarrhea. What is it from? It's from the toxin, okay? I got all kinds of good stories here. You're going to learn through the course of the videos that my family is like we're like case studies for almost all of these. But I'll tell you about the time I had ETEC in Guadalajara. Vibrio cholera, the quintessential cyclic AMP-inducing toxin. We're not just talking about watery diarrhea like, oh, I have to use the restroom. We're talking 20 liters a day. Lots of fluid loss, okay? So do these toxins work? Yeah, they work really well. All right, so you're looking down at the bottom, and you're looking at anthrax, and you're looking at Bordetella pertussis, and you're like, what? Those don't cause diarrhea. Well, clearly, really not. But what they do is, wherever their target organ is, they're going to do the same things. So what you see here, for example, under Bacillus anthrax, is you see that anthrax toxin, part of the anthrax toxin is a cyclic AMP-inducing toxin. And when you get anthrax, whether it's cutaneous, whether it's pulmonary, you get a lot of edema. Same thing, it's just not in the gut, all right? So that's the mechanism of the cyclic AMP inducers. And again, I would caution you to know specifically the mechanism, whether it's an adenylate cyclase, ADP ribosylation specifically of the G proteins, because again, Biochem likes to piggyback on that, and they'll ask specific questions about that in relation to, cholera or enterotoxigenic E. coli. All right, the cytolysins, again, we said weren't probably as important overall. Punching holes in another cell, all right. But for Clostridium perfringens, it's probably its most important virulence factor, okay? Without the alpha toxin, you're probably not going to get the symptoms of gas gangrene, all right? So in that case, it is clearly a very important toxin as far as a virulence factor, okay? For Staph aureus, again, probably the alpha toxin is not even going to come close to the importance of toxic shock syndrome toxin. Okay, so just keep those in mind.